recording. We have to compare what really is going on against what we expect to go on and see where those two things start to deviate from each other. And as soon as we find that deviation, that's probably when we've located our bug, and we need to fix reality to line back up with our expectations. And then once we know what's going wrong, we can fix it. So some advantages of using a debugger is that you no longer have any need to add or remove print statements to your code. I know when I first started debugging, I was the print debugger. I put print statements everywhere. But I would often find that I put print statements in there, fix my bug, take them out, run my program again. Oh, it's still breaking. And I need all those things back. So I put them all back in and then fix it and then take them out. And then in and out, in and out, in and out. And so it was a lot of like wasted time, like deleting the code and putting it back in. Or instead, sometimes it might be smart and just, comment out the print statements instead. But then I end up with like print statements all scattered throughout my code, and I'm generally probably lazy and won't delete them. And so now my code's a lot messier because there's just random commented out print statements everywhere. When you're using a debugger, you don't have to keep doing that. You have to keep putting them in and out. You can just say, hey, debugger, show me this, and it's going to show you that. And you'll be happy to see it. The other thing is that sometimes I've had it where I've added print statements and it's actually added new bugs. And this really happens a lot when I was doing like the C and the C++ programming, because I would screw up on a pointer dereference, or I'd actually have some small typo in there. And then everything breaks even more now, and I can't find that new error that I just put in there. If you're using debugger, you won't have these problems. If you ever need more information than what is going on, you can always ask for it. And we can also kind of go backwards a little bit in the program and see where we were called from. Before you can start debugging, there's a few things you have to do. First, you have to know what the right answer is supposed to be. If you don't know what the right answer is supposed to be, there's no way for you to debug because you don't know whether your code is doing the right or the wrong thing. You also not only need to know what the right answer is supposed to be, but what your code is supposed to be doing along the way to get to that answer, right? If you don't know what your code is supposed to be doing and what the variables are supposed to be, and like, where you're supposed to be at in your code when after you do step X and you're going to move to step Y, how are you going to know when it does the wrong thing? So you have to have a really good understanding of what's going on in your program for you to be able to debug at all. You also need some kind of input that's going to cause your program to break, right? Which is why it's really important to have good test cases and test cases that exercise the corner cases and really push the limits of what your code can do. Formal verification of code is possible. Like you can literally prove that this code is correct, but it tends to be a very expensive process to do it in terms of like computing power. And you generally have to do a lot of extra things too, and it just tends up being too much for people to do, and so we test. So we do our best idea of what we think, might be some inputs, what should work, what shouldn't work, and see if those things work. This is why you tend to end up with lots of buggy code, because someone forgot to cover some case. They didn't think of that until you accidentally did it, and that's why you have to go report to them what went wrong. So debugging is quite a simple process. You set breakpoints where you think things are going to go wrong. Display the relevant variables in your program. Step through your code until you find an error. Fix that error, and then repeat until all the errors are gone. So for our example, we're going to be working with an example where we're going to take in a list of numbers on the command line. So, oops, I need edit configurations. So we're going to take in this list of numbers on the command line, 12, 45, 3, negative 7, 8, 51, 23. We're going to then sort them in ascending order, and we're going to then print out the values. Everyone clear on what our goal is? So I've written some C code. It has some problems in it, quite a few actually, and we're going to try to use the debugger to figure out what's going wrong. One of the other nice advantages of the debugger is if you ever have segmentation faults, which a segmentation fault is simply accessing memory your program doesn't have permission to access. The compiler or the debugger can quite often bring you to that breakpoint, but not always. So if you're like Zig Faulting, you're like, where am I Zig Faulting my program? A lot of times we can just run over here and hit debug, and it'll bring us straight to that line of code. And then we can figure out what's going wrong. So let's try running our program and see what happens. And yeah, it just kind of died, right? Because we have problems in here. So there are three main steps in this program. First, we're going to parse our command line arguments. We need to turn them from their string representation into their numeric representation. We'll then sort them, and then we'll print them out. So if we want to set breakpoints, right, we can just click to the left of the line. And then we'll stop once we hit one of those lines. A good debugging strategy, if you have absolutely no idea of what's going wrong, is to set a breakpoint in the halfway execution point of your program. So halfway down. If you get to this halfway point and you see that everything is right, what must it mean? Our error must be in the second half of the program, right? But if we see that things are wrong, we know that the error must be in the first half, right? And let's say it ends up being the second half. What we could do is we could repeat the process, set a breakpoint halfway down here, and then continue again. If it's good, it must be in this portion of the code. Now my hand example kind of trivializes the problem because the problem generally, or I should say the execution of your program generally isn't halfway down your file, right? It tends to be somewhere in some middle of some loop or in some function call. So if we look over here at main, what seems to be the halfway execution point of our program? Yeah, right after parse args, right? Or right before we sort things, right in the middle. So we'll probably set a breakpoint here on line 66. Just going to click to the left of the line and hit debug. We didn't get there, so where do we know the error has to be at? Has to be in parse args, right? So let's go into here, and we'll set a breakpoint, maybe say on line 55, or I'll put a breakpoint here just so I can show some examples of some other things, and then press debug. So over here, you can see the values of my variables either down here or next to the variable name, which is probably a little bit bigger font up here. So when you reach a breakpoint, you have a few different options of movement. There, restart, which is restart the debugging process, restart the entire program. This is useful if you go too far in the program because there's no way to say like undo that last instruction. So if you go too far in the program, you got to restart the entire thing and begin the debugging process anew. There's resume/continue, which will bring you to the next breakpoint you would encounter in your program. So if I press that right now, my program's going to pick up and start running again, and the next breakpoint that it would end up hitting would be the one on line 55, and so it'll bring us to that line. The other ways we have moving are step over and step into, which they both do a single line of code. But the difference between these two is what happens if there's a function call on that line. Step into will go into the function, and you continue your debugging process inside of that function. While step over will go over the function and do the entire function and just move to the next line. So if I do step over right now, it's going to attempt to bring me to line 66 unless I hit some breakpoint in the execution of my program earlier. If I do step into, I'm going to go into parse args and continue my debugging from there. There's also step out of. Step out of will finish running the rest of the function and then go back to where it was called from. Do you guys have any questions about those methods of movement? So what should I use right now? Yeah. So step out of, what it will do is it'll run the current function that you're in and go back to where you were called from. So for example, if we were inside parse args and I do step out of, I'm going to go back to where parse args was called from, which would be basically line 66. I'll finish running my function and go back to where I returned to. I think he said somebody else had a hand. So should I use step over or step into right now? Step into, right? Or if I wanted to, I could also use resume just to get to that next breakpoint. So if I don't want to do each of these lines individually, I can just do resume. And now, bam, right there in this line. So down here, you can ask to display additional things, right? If their value is not already there. For example, if I wanted to, I could display like star len plus 5 times 3 minus 99 plus 24. I don't know why I would want to display that, but I want to let you know that the expressions here can be arbitrarily complex. You can pretty much put whatever you want there, and the compiler will or the debugger will display it to you, right? So when we get in here, some of the variables are automatically displayed. All the local ones would be. But as we continue the execution of our function, so scanf, what it's attempting to do is translate this argument, argv at I, into an integer, and then store the result into array at I. So we might keep stepping, and we find that it fails on the second operation for whatever reason. So now we need to debug once again and go back into it. So we'll press resume, and when we enter this for loop, what other things might we be interested in seeing that aren't already there? Maybe we want to see argv at I because we're using it, right? So if you don't want to type it and that expression is already there that you want to see, you can also highlight that piece of code, right-click on it, and say add to watches. So you can see that value showed up down here. And notice that the value of argv at I, what is it? It's the name of my program, right? Because if you remember, the first command line argument to your program is always the name of the program, right? So right here, I'm accidentally trying to translate this gigantic string into an integer, which is probably not going to work, right? Where does the first command line argument that you're really interested in start at? argv1. So how can I fix my code here? So if we set int I equals to 1, right, that'll cause us not to put any elements in position 0 in our array, right? And we want the first element to end up in position 0. Yeah, we can do argv at I plus 1. This will be perfectly fine because even though we've made len argc minus 1, so we won't go out of bounds, right? So this should all be cool. So now that we've changed our program, well, we gotta debug it again and see what's going on. I'm going to take out this breakpoint because I don't need it anymore. And we're gonna go in here, and now, instead of seeing argv at I, we probably wanna see argv at I plus 1, which is what we're doing. And you can see down here, if you can read the tiny font, that it's actually the number 12, which is what we should expect it to be. So if we step over, we attempt to do the copy, and then it dies on the first time around. So do you guys have any idea what might be going wrong? No, right? Remember, this is the line that we crashed on. It wasn't in doing the plus plus I up here. So I plus plus and plus plus I, we're gonna get the same effect. Any other thoughts? So when we talked about Scanf on Tuesday, what did we say that we needed to give Scanf for where we wanted to put the value at? We needed to give it the address of the thing, right? And notice, what value are we using right now? We're trying to say go put it in the address, right? The literal address array at I. So if we look at the value, array at I is 0, which is null. So we just said go write that value to null, which is always going to cause a segmentation fault because you cannot dereference a pointer to null. So what's wrong with this part of the scanf statement? It shouldn't say I, right? We want to put it into the element at position I, but we don't need the value of array at I. We need array at I's address, right? So we need the ampersand before it, right? This is a super common error that people make all the time. They're like, oopsies, they're used to doing prints all the time, and they just print the value of the variable, but scanf, it needs the address of the variable to put it into. So we've made a change. Let's try again. Any questions, though, so far? I put a lot of really subtle bugs in this program. So if you're not catching them all, it's understandable. It does take a long time to catch them, and most of you guys aren't like really fluent with C or really experts in it yet. So over here we do the first line, and after we do this line of code, notice that argv at I we got the 12. But as we go around again, we get the negative 53, or we get the 45. We don't really need this arbitrarily weird expression. We get the 45, and then we go again, we get the 3. Now we're trying to get the negative 7. We get the negative 7. Trying to get the 8. We get the 8. Trying to get the 51. We get the 51. Trying to get the 23. We get the 23. And it seems to have succeeded, even though there's actually still a bug here. We just have some undefined behavior. So because, for whatever reason, this time didn't actually trigger the bug, there is still one more error currently in this piece of code. And it's on line 54. Anybody here used malloc before? So you guys have a guess as what's wrong with this line? We forgot the size of the element, because when you use malloc, you say, I would like this many bytes, right? But you have to, each integer is going to be larger than a byte, so we need to multiply by the size of the number of things that we want. So the size of, and then we need some expression that evaluates to an int. So if you always want to get this correct, you take whatever's on the left-hand side of the equal sign and you dereference it one more time. So star AR will work, or I could also have written it, and I also could have written size of int, right? So I need len elements that are each the size of an int big, that many bytes. One way that you can prevent yourself from making this error is instead of using malloc, use calloc, because calloc takes 2 arguments: how many things you want, as well as the size of each of the things. So put calloc there, and then you won't accidentally forget to do that, because you always have to provide both the arguments. So now we've actually sufficiently allocated space for all of our elements. So now let's see if we can reach the breakpoint at the bottom of our function. Okay, great. We reached the bottom of our function, but we'd probably also like to see if our array is correct. For whatever reason, CLion doesn't have a way of displaying arrays, but you do have an interface into GDB. And if you want to see the value of a variable, you can just say p, which stands for print, and that variable. So if I do something like p star len, I can see its value. Now there's a special syntax that you can use to print single dimensional arrays, which you say print the name of your array. Where do you want to start at? I want to start at the first element. Then you can say at and the number of elements that you'd like to see. So I'd like to see len elements, star len, to actually get its value, because that's how many elements are in my array. And then boom, the value gets printed out: 12, 45, 3, negative 7, 8, 51, 23, which again, if we go back and we look at our configuration, numbers are there. Seem good? Any questions so far? Okay, so we can see that array has the right value. So maybe we'll resume our program and see if things work. And this is what I was telling you. So we have another Zig Fault, but CLion is able to point out to us where it's happening. So over here we have array at I greater than array at min index. This is Zig Faulting. So we might want to look at what is array to see its value. So array, if we look at it, its address is 7. That should be really suspicious, because most of the time when you have an address, it's going to be a very large, big, weird thing, not something this small. So we probably made a mistake. One other thing I want to point out before I forget is if you look down here, you can see the call stack, which is the series of function calls that are currently executing to get to the point where we're at. If we want to, we can go back up and see what's happening at a higher level. So here we can go back to say get sorted, and we can see all the values in this portion of the program and what they are. And again, we see that array is 7, which means we must have passed the 7 from the level above it. So if we go back to main, we can see that array is 7, right? But we were trying to modify it here inside our function parseargs. So let's see if that actually happened. So we'll restart our program. And down here, if we look at array, well, what's array's value? It's OX600 something, right? Some big weird value, which is what the value should hopefully be when we return. So if we go out of our function, we come back here and array is 7. And if we go to print the values, we saw before that they were correct. If we print them here, again, we can't access address 7. Something's wrong with the address. Does anybody have a guess as to what happened? Again, this is another C subtlety, not an easy one. So here's the thing. In C, if you want to be able to modify one of your arguments, you need to pass a pointer to that argument. You need to give its address, right? The reason that we were able to change len in this function is because we passed the address of len into our function. So we passed a pointer to that object to be able to modify it. An example of this happening, we can kind of see, and a really useful website is called, let's see, it's called Python Tutor. Don't get weirded out by this, the name. It actually can do C code. And so what we can do is we can try pasting some of our C code here to get a better insight into what's happening, but only the portion that we're actually interested in running. Here. And we can't actually use argc and argv over here in C, the Python tutor, so we're gonna have to make our own. So char star argv might be equal to the array of strings. Maybe it's 12, 7, and 9. And we also need one more, which is the name of our program, so we'll just call it prog. And then over here, argc will be equal to 4, so we can test this out. Thank you. We would have concatenated those strings together. So I forgot a semicolon here. Oh, right, we're only going up to parseargs. You have to give it a moment when it does it, but it tends to be pretty useful. So over here, right, we can see that we start in main. Here we have our array, which is full of all of these strings. You can see them there. Then we have argc. It got filled in with 4. Array and len, their values are unknown because we didn't say what they're supposed to be. And now we can call parseargs. So notice that we created some new variables. We have a new argc, a new argv, a new ar, and a new len. This is because in C, arguments are passed by value. So we create brand new copies and copy in their values. So argc got the value 4. Argv ends up being a pointer to this array that we had back here in main. So the argv in main. And then we say star len is equal to argc. So notice that our len right here in the function we're working with, where's it pointing to? The len back in main. Right? So when I do this line of code, I changed it to B3 even though this arrow's in the way. And I can't move it, sorry. So we go through here and we make some more space. And we should have that AR is equal to that space. So now we have I, and we should be filling in the values, though I don't know why we can't see where those things are at. and then it finishes and it goes down here. But notice we never changed AR back out here in main. So your rule of thumb that you want to follow is if you need to modify a variable of type x in your function must accept at least a pointer to x. So back here, since we wanted to modify len's type is int, so our function needs to accept a pointer to an integer. All right, we'll pass back over here. Right? Here, len is an int, so if our function wants to be able to modify it, we need a pointer to an integer. If we wanted to be able to modify a character, our function would need pointer to a character, right? Remember, if you want to modify something of type x, in this case x is char, then we need at least a pointer to that type. So if we want to modify a char, we need a char pointer. If we want to modify a double, we need a double pointer. If we want to modify AR, whose type is integer pointer, we need a no, not a pointer to an integer, one more star than its type. So we need a pointer to an integer, or an integer pointer. We need 2 stars here if we want to be able to modify it. So generally, like speaking, if you want to modify something of type x, just one more star than what x's type is in the function. So since out here array's type is integer pointer, this actually needs to be integer double pointer for things to work. Yeah.
Sorry, I don't know how we spoke to this. Can you explain what the star is?
We'll probably be talking about that tomorrow in class. But a pointer simply holds the address of a variable. So it tells you where at in memory that thing is.
That's what the star is?
Well, the star is used in 2 different contexts. One is to declare the type of a variable, right? So if you see type star, that means that this variable is a pointer to an integer. You kind of read it backwards, right? So AR is a pointer to an integer. It holds the address of an int, right? And so over here, to make this work correctly, we need to have a pointer to an integer for things to work correctly. And this is probably going to be something that you're going to have to kind of like do a little bit of research on your own or stop by office hours to get help. And we'll try to slam through it tomorrow. But I'm trying to condense basically a 10-week course worth of material into like 3 lectures. So it's not going to go smoothly. But at least I said it. But come get help in office hours. Go look online about pointers and how they work, and you'll probably be feeling a lot better. So for things to work correctly, we need a star here, which means we need to add some extra stars down here. Because calc, we want to make integers. So we actually need to say, go to where AR is pointing, and make it to be this much space. And we need to add an extra star here to match. Then over here, we need to leave this ampersand here, but then we need to dereference AR so that we actually get where AR is at, then get the ith element past there, then get its address to go store it in the right place in memory. Finally, the next error is we need to put an ampersand here to pass in the address of AR. So if we go over here and we go back to Python Tutor, just to kind of visualize what's happening a little bit better. Oops, not the whole thing. And then we need an ampersand here. And we visualize our execution. So now notice that when we go inside of our function call, notice that we have our pointers. Notice that our pointer AR points back to the AR in main, which is what our original intent was, because now we're actually going to modify what's over here in main. So when I go and I create the space, you can see, great. AR up here, it's now pointing to that space, this array of numbers. And now when we go to fill it in, hey, it's getting filled in. You can see it's changing down here. The 7, and then the 9. And then we finish our function, and now when we come back to main, hey, notice our AR in main, it's actually pointing to those values, 12, 7, and 9. So again, you're like, man, see, how can you have so many errors in like 5 lines of code? It's really easy to make these mistakes. Yeah.
I saw a confusion.
Mhm.
So when we had these errors and you still printed out the values for AR using GDB.
GDB.
Yeah. Well,
Why did it work?
Yeah.
It worked here before because when I printed out the values the first time, we were inside this function and we changed the copy to actually point to the elements. But we didn't change the original, right? You've probably had it in Python where you had like an argument, and if you have like your argument x and you say x equals 10, well, when your function comes back out, whatever thing you pass in there is not 10. It's whatever you passed in to begin with. So same thing was going on here, right?
Okay, so
Right? If we have like def, our fun takes x, and we just say x is equal to 10, and over here I have y is equal to 20, right? If I say fun on y, what's y's value? It's 20, right? Because it got a copy, right? The same thing was happening here. We got a copy, and if you look inside this function, you ran it through a debugger, you would see that inside the function, yeah, x got changed to 10, but it was a copy of the original, not the real thing. Python's a little bit more subtle than that, but it's the same kind of idea as what was going on before. So when I printed out the copy, yeah, everything was fantastic. But when I got back to the original, it hadn't been changed, and so it didn't have any new values in it.
so also so if it's in the curly braces, it won't work because it hasn't changed the original and it's only printing out the copy.
We were printing out the copy because if you're talking about the curly brackets for the function.
Yeah.
Yeah, I'm still inside the function on this line. I haven't left it yet.
So that's why it worked, and
Mhm.
that's why when we're outside it changed it to copy.
Well, like, because again, like we'd modified the copy of the variable inside the function, and then when we left the function, the original was left unchanged and didn't have the values that we wanted.
But in the previous example, if you return the value of the x as a function, then does the actual y change?
So if we have, def fun x, right? X is equal to 10, print x, return x, right? So over here, if I say fun of y, notice that we're going to print 10, and this was the value that was returned. So we see the second 10. What's y's value? No, it's 20. Where did I say y equals the return? It didn't. Right? If I wanted to change y, I'd have to say y is equal to the fun of y to actually get y to get set to whatever the function returned. So now y is 10 because I changed it. Okay, so great. We fixed most of the most subtle bugs in our entire program. So let's see if it works. No, it's still crashing. So let's take this breakpoint out and try debugging it. But now again, the debugger was able to point out exactly where segmentation fault is happening. If we look at the values of the variables here, do you notice any of them that seem suspicious? Which one? Which one? Oh, the errors have, these ones down here, no, these are just because they're not able to create them. So look, you can see there's only 2 local variables. There's AR, there's len, and there's I. So which of these look like they have a crazy value in them? I, right? AR, that's what pointers look like. They have big weird addresses in them, right? But I has the value of negative, 41,253. and I'm trying to get my array at negative 41,253. Which is probably going to cause problems, right? Because my array is only 7 big, and in C, you can only use positive indices for arrays. You can't use negative indices. So what's wrong with our code? It should be plus plus I, but we wrote minus minus I. So just a small mistake there. So plus plus I. Plus plus I, again, is essentially I plus equals 1. So we run our program again, and we get 51, 51, 51, 51, 51, 51, which is not the right answer because there are other numbers besides 51 in our array, right? But hey, things are printing out right, so where do you think our error probably happens to be? Not in parse args, right? We just finished debugging that one, right? It's going to be like getting get sorted. So let's set a breakpoint in here, debug, and see what our values are. So when you're debugging, you should try to do as big of steps as possible to limit the amount of time that you spend looking at correct code. Because most of the code that you write, believe it or not, is the right thing. It's going to work. There just tend to be a few small errors that make the whole thing fail, right? So over here, instead of going directly inside of min index of array, which is going to find the index of the minimum, we should just step over it and see if we get the right value. But before we execute the code, we should kind of figure out what the right value is supposed to be. So to figure that out, we need to see, well, what is AR? So again, if we run over here to GDB, we can say PAR0 at length. So here's our array. What's the index of the smallest element? 0, 1, 2, 3. So when we do this function call, we should expect min index to be 3. So let's see if we get that. So I'm going to do step over because I don't want to go into the function right now. And we look and we get the min index back, which is 5. That's not 3. Right? 0, 1, 2, 3, 4, 5. That's actually the index of 51, which seems to be the biggest element in there. So we're going to need to set a breakpoint on min index of array and see if we get the right thing and what ends up being wrong. Yeah, I mean, you already saw it, right? The mistake, as was just mentioned, is, oopsies, got the sign the wrong way. I'm actually finding the index of the biggest thing, not the index of the smallest thing. So let's try flipping that around. Oops. And rerunning our program and seeing what we get. That doesn't seem right either, right? But we now need to go and debug a little bit more and see if we end up getting the right thing. Okay, so now when we call min index, again, we said the first time that we call min index, we should get 3. And what do you know? We get 3. The way that this sorting code works, to give you an idea, is we first find the index of the smallest thing. Then we're going to find, then we're going to copy the element over to sorted. And then what we end up doing is swapping the index that we found, right? Or swapping the element that we found with position 0 the first time. So we end up putting the smallest thing at the beginning. Then the next time around, we want to find the second smallest thing, copy it over to sorted array, and then also put it into the second position of our original array. Then find the third smallest thing from among the remaining things and do it again and again and again. So over here, we should see what we're trying to swap. So right now, I is 0 and min index is 3, right? So we should be trying to swap elements 0 and 3, and let's see if that happens. So here, again, we can print out our array. Yeah, 1 second. And then if we complete this line of code, again, we should expect the 12, the -7 and the 12 to swap spots. So let's print out the value again. And the 12 and the -7, do they swap spots? No. So where do we know an error must be at? Swap, right? Because nothing got swapped after we did it, right? What was before was the same thing as what was after. Yeah?
How do you find the smallest thing in the array?
You keep looking through the elements. So you originally assume the first element is the smallest, and you keep going through, and if you find an element that's smaller than the element that you think is the smallest right now, update it to be the smallest.
Oh, nice.
So your classic find the minimum. So let's go and go over to swap. A shortcut that you can use in C-Line is you can click on a function and do Control B, and it'll jump you straight to that function that you have. So we set our breakpoint here, and we restart. And let's see if things work. So we're going over here to swap. So over here we have a pointer to A, which is pointing to 12. And over here we have a pointer to B, which is pointing to that -7, right? So we can see that our arguments are correct. We're pointing to the right things. I now create temp. Temp starts as pointing to wherever A is at. But now I say A is equal to B. This will make A point to B, right? But it's not actually going to do the swap. And then I can say B points at temp. So yeah, B points at the 12, but the original elements, they haven't been modified. I've just changed where these pointers point to. So any thoughts on how I might fix this code? We need to dereference our pointers. We need to say, go to memory at that location and change the value. So the mistakes that we made here is that our temp should be an integer, and it should be equal to the value that A points to. That's what the star in front of the variable means. Whatever the value in memory at A's address, we should copy that value into temp. Now over here we're saying go to wherever A is pointing to and make its value be equal to wherever B is pointing to. Then we should make whatever B is pointing to the value that we have in temp. So that's the change that we need to make here. And again, swap, this function is something that I recommend that you do put into Python Tutor so that you can see it actually being done with the pointers pointing to each of the elements. And I guess, since I said that we should probably do it, let's do it. Just so that you guys can get a little bit better of an idea of what's going on. So over here we have swap. So now over here we might have like our int x, which is equal to 7, and y, which is equal to 9. You can declare multiple variables in the same line, just separate them by commas if they have the same type. So now when we swap, right, our function wants a pointer. So how can I get a pointer to x? Right, we want x's address, ampersand, right? Remember, one way to kind of think about it is whenever you put a star in front of the variable, like here, it removes a star from the type. So if we look at B's type is int star, right? If we have star B, though, we remove a star from the type. So after we remove the star, what do we get? We get just int, right? Which should make sense. We want to change an integer. When you do the ampersand, you add a star to the type, which you can only add at most one star using the ampersand. Because again, you can't ask for the address of an address. Doesn't really make sense. Like, what's the address of your house? Good question to ask. What's the address of your house's address? That's a nonsense question, right? So don't ask the computer to do that for you. And then ampersand y over here. So let's visualize our execution and wait a little bit. So over here, right, we have main. So we make two variables, x and y. They had the values 7 and 9. Now when we call swap, right, we create two pointers. Well, where's A going to point to? A is going to point to x, and B is going to point to y. So now I create a new variable, And my variable temp should have the value of whatever a points to. So what does a point to? 7, so temp should end up being 7. Now over here I'm saying change whatever a points to be equal to whatever b points to. So over here we're going to go to where a points to. Gosh, a points to, it points to the x, right? And we're going to change it to whatever b points to, the 9. So you should watch and you'll see the 7 is going to flip to a 9. Right? Then we say take whatever b points to and change it to be equal to whatever temp's value is. So b is pointing back here at the 9, so its value is going to change to be equal to whatever temp is, the 7. And the values were swapped. Yeah?
So what's the difference between changing the pointer and changing the actual value?
What's the difference between changing the pointer and changing the actual value? So let's go and redo our code and have it go back to being the wrong version.
Okay.
Right? So over here, if we switch it back to what we originally had, right, we had integer pointer temp equals a is equal to b, and then b is equal to temp. So let's visualize the execution now. It's a good question, right? So again, x and y get created just like they did before. We pass in their pointers. A is going to point to x and b is going to point to y. So now over here we said temp is equal to a. So temp is going to point to wherever a points to. Oh, temp also points there. I don't know, it's hard to see, but it is also pointing there. They're all both pointing to x, right? Then we said a equals b. So now a should point to wherever b points to, right? B is pointing to the 9, right? It's pointing to the y. So now a should also point to the y, right? Then b should point to wherever temp is pointing to. Temp is pointing to x. So b should also point to x. Now we finish. Notice, did we ever change x and y? No, we just changed where the pointers point to. These temporary variables that only exist for the duration of the function. So we go back from main, and the values weren't swapped. I know, right? It's fun. Agreed. So we really don't have any more time today. Again, if you're struggling with the C code, do some research on your own. Do see some examples, especially searching for things about pointers and memory management. And then also stop by office hours. I'm more than happy to run through additional examples with you.